Oh, hey, it's time for more calculus. Today, I'd like to work with you on the last section in our textbook under derivatives, and we're going to talk about section 3.10 related rates. This is the last section in the Rogawski textbook that we've been working from this semester. And I think this content is really super cool. I spent time talking with my friend Evelyn Lamb earlier today. She's a writer, a math writer. She writes for Scientific American and some other journals about mathematics and science. And she said that when she took calculus, this was one of the parts that she really enjoyed. So I'm really happy to share this with you today. The major lesson that we're going to take away from this content is how to approach these word problems, because the related rates problems are word problems, and I think they're really super cool. I do have 3 videos on YouTube, links right here, that I would invite you to visit. These are in addition to the problems that I'm going to do in here. So if you want to see more examples of worked problems of related rates, I would invite you to check those out too. There are, of course, a bunch of YouTubers out there who have videos about related rates. These ones are, they're cool problems. I hope you like them. So I'm going to start by talking through some advice, and then we'll kind of practice on 3 problems, and then we'll call it good. I want to say that related rates problems, they're word problems, and things are going to be governed by an equation, and some things are changing. And the word related rates comes from the fact that the time rates of change and the problem are related by an equation. That is to say, the rates of change are related to each other through an equation. They're related rates problems. I should avoid dropping my stylus. So, let's talk about. Let's practice some advice for how to do these problems, and then maybe you could refer back to this advice as you try them. Everybody's method's probably a little bit different. There's some advice given in the book. The book gives a 3-step process. This one that I've given here is perhaps 5 steps in length. Every problem for related rates is a little different. Different problems require their own tactics. And how are you going to get good at doing these is just by trying a lot of problems. And our textbook I'm looking at our textbook right now. Our textbook offers 39 problems. There are additional further insights and challenges. So tons of ways for you to get practice on these. Start with the easy ones so you can get the hang of the pattern, and then try some hard ones and build your confidence by doing some of everything. So my first point of advice is I think you should draw a picture. I think that everything starts with a picture. And I think you should label absolutely everything that there is to label in the problem. If there's a way that you can figure out what it is, you should just label it. I really like drawing arrows to indicate that there's action. So if something is moving to the right, I'll draw a right arrow, and I'll try to label that with what it represents. So if that's some quantity, let's suppose that that's some quantity P, and P is moving, then the speed of P is going to be dP dt. And I think that that's really important because we're all about rates of change here. I think it's also really important probably to establish where 0 is and label some axes. Giving yourself that frame of reference, I think, is pretty critical. I think that you should definitely identify the target unknown as part of this process. What's the goal? What are you doing? Oftentimes figuring out that and answering that concretely is the key to solving these problems. The second thing that we're going to do is we're going to relate the variables. Relating the variables, what I mean by that is we're going to write down an equation. Or two. Maybe there are several equations that you need in order to be able to do this. And things that are implicitly functions of time I think is important. So you might remind yourself, be like s equals s of t, to remind yourself that the state variable s is actually a function of time. Implicitly differentiating is the third step. For that, I think you should see section 3.8. That's 2 lectures ago. The main point of that is that when you take derivatives, you've got to chain out the derivatives of the implicit functions. Finally, steps 4 and 5 are like solve the problem, kind of. So we're going to do our best to substitute in known quantities to the equations that we have. And we might also have to use that equation in various ways. And then we'll solve for the target unknown. And I feel like this is pretty good advice. And the best way to actually do it is to just practice some problems. So let's do 3 problems together for related rates. So let's turn the page. Let's do our first example. My examples are numbered here according to, this is the number in the book. So that's example 1 in the book. It's also my first example here, so that coincides, yay. So let's read the problem together. Water flows into a cylindrical container at a rate of 5 cubic inches per second. The container has a height of 6 inches and a base of radius of 2 inches. At what rate is the water rising in the cylinder? In order to make sense of this, I really think that the first thing that we should do is draw a picture and label everything. We're going to draw and label. Let's see here. Water flows into a cylindrical container. Okay, cylindrical container. Got a cylindrical container. Here is a cylindrical container. We're going to draw everything and label it. Okay, so the container has a height of 6 inches. And the radius here is 2 inches. I often, when I'm doing one of these problems, I'll omit my units of measure because I think that they end up cluttering things quite often. So I often will omit that. Okay, I think that there's a little bit more that we can label in this problem. I want to label here. Let's call that height W. That's the height of the water. And there's, say, a faucet or a spigot, and water is flowing out of that spigot, and water is flowing at a rate of 5 inches cubed per second. Whatever, I'll put my units back in here. And the origin is right here. I think it's important that we attempt to label the unknown that we're trying to find. Label the target unknown. And in order to label the target unknown, we really need to identify what the unknown is. At what rate is the water rising in the cylinder? Let's see here. Well, I think then that we need what rate is the water rising in the cylinder? We really need to find, I think, then dW dt, because that's the height of the water. At what rate is water rising in the cylinder? Okay, so that means that our target unknown, so this is rising right here with rate dW dt. I want to find dW dt. So I think that we should probably start writing down some stuff. I think we should make a note that this rate right here, that's a volumetric rate of change, right? Right? So that's a volume, which means that this quantity, this 5 cubic inches per second right there, that must equal to dV dt. So I think that we're going to write down our constituting equation, our governing equation, is going to be something about the volume of a cylinder. So I'll call that V sil. We'll just call that V so I don't have to keep writing the sil everywhere. But well, I think that adding a little subscript is pretty nice. Okay, the volume of a cylinder, put this on a sheet that you refer to of common measurements of things, formulas of things. The volume is going to be equal to pi times the radius squared, that's the cross-sectional area of the cylinder, times the height of the cylinder, or the height of the water. So this is how much water there is. And so this is our governing equation right here that relates the volume, the radius, and the depth of the water. And so I think that we should check back to our general instructions on the previous page. Let's see here. Draw a picture and label everything. Check. Relate the variables. We just did that. Check. Implicitly differentiate. Okay. So now let's implicitly differentiate. So I'll call that equation 1. So we'll implicitly differentiate equation 1. You might find it helpful, I don't know, but you might find it helpful to note that volume is a function of time and W is a function of time. Those things are both changing. The amount of volume in the cylinder is changing, as is the depth of the water. And the radius right here, that's a constant. So let's implicitly differentiate number 1, and we will get number 2 on the left-hand side. So on the left-hand side, I have V, and the derivative of that is dV dt. And on the right-hand side, I have pi r squared times dw dt. And why did I get to just do that, this part right here? Those are all constants. And the only thing that varied is the W. Okay. I really like to periodically refer back to what my goal is. I have in green highlighter, what's the rate at which the water is rising in the cylinder? I want dW dt. This is my goal. I want that. So now we just need to figure out, hopefully I have the other pieces. Do I have dV dt? The answer is yes, I absolutely have dV dt. That's this 5 cubic inches per second, the rate at which water is flowing into the container. So I know that that's 5 cubic inches per second, if you care, equals pi times R is 2 inches times dW dt, which again is my goal. So I'm going to solve for this piece right here. So I'm going to have that 5 over 4 times pi is equal to dW dt. and that number is about equal to 0.4 inches per second. Okay, so let's turn the page and try another problem. This is example 2, filling a conical container from our book. This is on page 198. If you want to see how our textbook author solved it. I chose to use oil instead of water, whatever. Okay, so let's read this out. Oil flows into a conical container with the point at the top at a rate of 5 cubic inches per second. The container has a height of 4 inches and a base radius of 2 inches. Show that the rate the water level is rising depends on the level of the water in the container, and that it rises faster the higher the water level. Okay, so this is kind of my goal. I'll highlight my goal as this stuff. That's my goal. I'm going to show that the rate the water level is rising. Okay, so our goal is the rate the water level is rising. Okay, well, we need a name for it, and I think we should call it dW dt for the water level. So there I kind of named things before I even drew a picture, and that's cool. So let's go ahead and draw a picture of what this looks like. I've got a conical container with a point at the top. Okay, conical container with a point at the top. Conical container with a point at the top. Let's draw a cone with a point at the top. We've got, there's the little waves to indicate the depth, and the cross-sectional area is a circle. Let's label some stuff. Right here, this radius equals 2. The total height right here is equal to 4. And that distance right there is what we're going to call W. And let's say that there's water flowing in from a hose. And water is flowing in at a rate of 5 cubic inches per second. Seems like a lot. We are interested in the way that W is changing, right? I like using action arrows to indicate that something is moving. dW dt, because W is changing. Okay. So I think what we're trying to do here, we should try to restate our goal. Our goal is to show that the rate the water level is rising depends on the level of water in the container. Okay, so our goal is a formula for dW dt, and show it depends on the level of water in the container, W, and that as W increases, dW dt increases also. I think that's our goal. So we need to derive a formula for dW dt. Okay, so we need to figure out something that relates these. Again, I happen to have here a volume rate of change. And I believe that we should call that dv dt. So there are, let me label it blue here. Here's the part that has the oil in it. Oh, I have oil and water showing here. That's fine, whatever. Serves me right for changing one word and not all the other ones. Okay. I just really wanted to work with oil. Particularly olive oil. Olive oil is delicious, isn't it? Okay, so there's the top of the cone, and then there's the rest of the cone. And the part that we're interested in is the stuff down here. This right here, the stuff on top is empty. Okay? And the volume is this part down here. That part in the top is empty. So, I need to figure out how to write that volume, and I can totally do that by taking V equals the entire cone minus just the part at the top. I know I'm just drawing it as pieces of a triangle, but that's okay. I think it gets the point across. So what's the volume of the entire cone? Well, okay, so I've gone and looked up volumes of cones, and I remember that this is 1/3 times pi r squared times h. What's h? 4. R is 2. Minus 1/3 pi something times something. So we need to work on how to get the radius just of this smaller one and the height of just that smaller one. I think we can do that. Let's work on that on a side picture over here. So let's draw a triangle. Let's call that 2. Let's call that 4. We have this smaller one. This right here is what we were calling W, which means that that distance there is 4 minus W. Because the total height is 4. Now, I need you to remember something from geometry, and that is similar triangles. Similar triangles have ratios of side lengths preserved. So I could write that 2/4 is equal to, so 2/4 is this one to this one. So then we're going to be talking about that one to that one. That one to that one. So how about we name this right here? And let's just name it some little like placeholder name for now. How about we go Q is equal to Q over 4 minus W. So that means that Q is equal to 1/2 times 4 minus W. All I did there was simplify that as 1/2, and then I moved that to the other side. Okay, so we were able to discover in this expression right here that that's the radius of small triangle, or Q, is equal to half of 4 minus w. So let's put that in. And then what's the height? 4 minus w. Okay, it kind of looks like I have too many variables inside this expression for the volume, but I don't, because this r, we know this r is equal to 2, and I know this h is equal to 4. So the only variable here is my w. Furthermore, one thing to notice is that as w goes to 4, this 4 minus w here goes to 0, and I'm just left over with the volume of the full conic space. Let's go ahead and substitute in our actual values. I know that r is 2. I know that h is equal to 4. And then we'll kind of let the chips fall as they are. So we'll have that the volume is equal to 1/3 of pi times 16. Let's go ahead and write that as 16/3, shall we? 16/3 of pi minus a third of pi times, we could take that half and we can merge that together with that third right there. But that half is squared. Let's do this step by step. Let's not get ahead of ourselves. A third of pi times 1/4 of 4 minus w squared times 4 minus w. And at this point, some of those parens are unnecessary, and so I'm going to erase that one and that one. Missing my operator here, times. There we go. This is looking pretty good to me. I'm feeling pretty good about this. Let's rewrite this one more time. Let's write this as v equals 16/3 pi minus a 12th of pi times 4 minus w cubed. Again, what's our objective? Because I kind of feel like it's easy to lose track of that. Our objective is a formula for dw dt, and we need to show that it depends on w. And furthermore, that as w increases, dwt increases. Okay, so we're going to use this expression here. We finally have our equation that relating state variables. And when we have that, our next step is to differentiate. On the left-hand side, I'm going to get dv dt. On the right-hand side, the derivative of this constant is equal to 0 minus the 12 pi is for free. And then we've got to do the chain rule on this piece right here. So let's do the chain times 3 times 4 minus w squared. And now we're going to chain out the derivative of the inside, and that's going to be times minus dw dt. So now let's simplify this expression. Let's call that dv dt is equal to, let's see here, I've got a minus and a minus, so we'll plus those. So I'm going to have, and that 3 is going to merge with that 1/12 to be a quarter of 4 minus w squared times dw dt. And now let's divide it and put it over here, because we're solving for our unknown that we wanted, dw dt. That's our unknown that we want. We want a formula for it. And check it out, because we kind of have like a lot of things going on here. I want to remind you that we were given dv dt. That was given. That's 5. So this dv dt right here is given. That's equal to 5. So I'll have 5 over a quarter of 4 minus w squared equals dw dt. And I just like to merge those together. This divided by a quarter, we're going to flip it and put it up here. And this will turn into 20 over 4 minus w squared equals dw dt. Now I wanted green. Because that's our unknown. Okay, so our goal was to get a formula for dw dt and show it depends on w. Okay, I think that we can call that good. dw dt clearly depends on w. And as w increases, dw dt increases. So let's examine this expression. As w increases, does dw dt increase? Well, I think that here's a way that you could think about that. Well, as w increases, but w has to be less than or equal to 4, because that's the design of the tank. Like, the tank can't hold more than 4 units of height of water. Okay? So as w increases, but w stays less than 4, 4 minus w is going to go to 0, and it's doing that, and 4 minus w is always positive. So that means that we're having 20 over something going to 0 from the positive side. So I have 20 over a small positive number. And that is increasing as w is increasing. If we wanted to look at a plot of this rate of change as a function of w, not as a function of time, but as a function of w, we're going to approach a vertical asymptote at w equals 4. And it's going to do so as a square function. So as w increases, and we're plotting dw dt on this axis. This is this curve itself is dw dt. So as w goes to the right, this curve goes up. So yes, this is increasing as w increases. And I think that about covers that. Pretty different in character from the first problem, but kind of similar. Let's do one more. A spy uses a telescope to track a rocket launched vertically from a launch pad 6 kilometers away on perfectly flat ground. At the moment when the angle theta between the telescope and the ground is pi over 3, the angle is changing at a rate of 0.9 radians per minute. What's the rocket's velocity at that moment? I'm going to highlight that in green because that's what we're trying to find. And I personally have no hope of solving this problem unless I draw a picture first. So, let's draw some coordinates. Let's put 0 here. Let's call this, say, x. And let's call this, say, y. Let's put our spy here. And they've got a telescope. And let's put that telescope here. That's their telescope. And they look in a straight line with the telescope. And they can see a rocket. And that rocket is 6 kilometers away. Let's see here. What's the rocket's velocity at that moment? We're not done labeling things yet. We still have stuff that we haven't labeled in our picture. We haven't labeled the angle theta between the telescope and the ground. Let's go ahead and do that. Let's label that right here. That angle right there is we're going to call theta. And at the moment we're thinking about, that's equal to pi over 3. And this height right here is, let's call that y. And what are we interested in? We're interested in the velocity at that moment. So I want the velocity at that moment. That means I want dy dt. So let's draw an action arrow and label it as dy dt. As the rocket increases its height, this angle is going to go up, right? When the rocket is way up here, the angle has to be there. And when the rocket's down here, the angle isn't very high up. So as the rocket goes up, that angle goes up too. So I think my labeling of this theta with an arrow was appropriate. So so that's changing. And that's changing. We drew the action label there. We kind of have an action label here, but I don't think that we've labeled the rate of change of this angle. And so I think I want to draw that and call that d theta dt is the rate of change of how fast the spy has to change the angle of their telescope. And we're told that that angle is changing at a rate of 0.9 radians per minute. So this is equal to 0.9 rad per minute. Oh, it's snowing. Cool. I have a window in this room. I hope you have a window in your room. Okie dokie. So let's label the unknown. I want that. That's my goal. I want dy dt, and I've got this. I've got this relationship right here. So now we're gonna have to recall some trigonometry And I think that we should probably recall SOHCAHTOA. Yep. So I want to relate theta and y. All right. I think we should do that because I've got this angle right here, and I've got the opposite and the adjacent. I don't know anything about the hypotenuse. The hypotenuse is a big question mark, but I know that the opposite and the adjacent are labeled in my diagram. So that suggests that from SOHCAHTOA, I think I'm gonna use that the tangent of theta is equal to, let's see here, opposite over adjacent, TOA, y over 6. So this is my governing equation. We always arrive at one of these when doing one of these related rates problems. And now the next step, see if you can predict my next step. My next step is going to be, I'm going to differentiate it. Because I've got theta of time and y as a function of time, right? They're implicitly functions of time. So now I'm going to differentiate with respect to time. And now I need the derivative of tangent. I'll go ahead and write down that d dt of tangent of theta is equal to d dt of y over 6. That means that secant squared of theta, chain it out, times d theta dt is equal to dy dt over 6. What are we going for? Oh, no, that's not what I wanted to do. That was the wrong tool. It was dy dy. No. Come on. dy. Boop. dt. Thank you. I wanted that tool. That's our goal. I think that repeatedly highlighting what our goal is it's a really good tool. At least for me. I hope it is for you. Okay, so let's try to figure out, do I know everything else? D theta dt. We can refer back to the picture or to the problem statement. I know that that is 0.9 radians per minute. 6 is just 6. And theta is equal to pi over 3. So I know everything except the goal. Well, that's good. Because if I didn't know something, then that'd be a problem. Sometimes it might look like you don't know something, and then you might have to go use the governing equation to figure out what it is. So we are really close now. I'm just going to plug everything in that I know, and I'm going to solve for dy dt. So I have that secant squared of pi over 3 times 0.9 is equal to dy dt times 1 over 6. It's just another way of writing the same thing. For the secant squared pi over 3, let's figure out what that is. Secant squared pi over 3 is equal to 1 over cosine squared of pi over 3. I've got my circle. Pi over 3 is down here. Cosine, I think that's root 3 over 2. Yeah, because otherwise it'd be half, and root 3 over 2 is bigger than 1 over 2. That's totally it. So this is equal to 1 over root 3 over 2 squared, which is equal to 4 4/3. Yep. Did I get that right? I kind of think that my cosine is off. Why don't you go ahead and pause the video and get out your unit circle and double check what that. Go ahead and check what that value is. So we need to figure out what cosine of pi over 3 is. Oh, it's a half. It's a half. I do apologize. That drawing was not helpful today. I think it's time for dinner. Oh, pi over 3 is up here. It's not down there. Yeah. Yes, it's a half. Okay. So this is over a half down here. So I have that 4 times 0.9. Ooh, let's multiply by 6 on both sides. Equals, dy dt. Dy dt, that's what I'm trying to find. Okay, so now I just got to do this. I'm going to run that through my calculator. That's going to be 24 times 0.9. That's 10% less than 24. So that's 24 minus 2.4. Yeah, is 21.6. Yeah. Kilometers per minute. Yeah. Ooh, is dy dt. That was what I wanted. 21.6. The answer, 21.6 kilometers per minute. It's pretty fast. Okay, what do you think about that problem? I think that problem's really cool. There's like an infinite number of problems that we can come up with. Don't take, because you've seen these 3 in a video, don't think that means you know how to do these problems. I feel like if you engaged with these problems and you thought through them as we work through this note sheet, then you're in a good state to try some other problems. So I would encourage you to next. I want you to try example 3 from our book. That's on page 100. No, that's on page 200. I worked problem or example 5. Which is on page 201 in one of my YouTube videos. I did another problem in one of my YouTube videos also. I feel like watching videos is insufficient to really get people to know how to do these. It's really, you got to try these. You got to do these problems in order to really master them. Just watching videos isn't going to get you there. I think I'll stop there and say thank you very much for watching these 3 examples. And I'll hope to see you in class to answer any questions you might have. Thank you so much. I'll talk to you later. Bye.